Welcome back, everyone. In the past session, we talked about gradient boosting. So that's really the topic that we mentioned, went into great length, gradient boosting or gradient boosting machine. Just to refresh your memory, the basic idea of gradient boosting was to it works for both regression as well as classification. And the fact is that it sequentially add predictors. Now, every time you add an additional predictors, it corrects its predecessor. So it keeps fitting new predictors to the residual errors. So the steps that we talked about here, really, it looks like this. Is basically the final function is fx, which is what we fit initially. The gx fits into the error that's left over from step 1. The hx fits into the error that's left over from step 2, and on it goes. And you can do further weighting. So the basic ideas really is that it learns from the mistakes it made and continuously improve from there. So today, the sessions that we're going to go into is called extreme gradient boosting. Now, this is literally the cutting edge, the very top end, at the sharp end of the machine learning algorithm. And literally, most of the competitions are won by using extreme gradient boosting. Now, there are a lot of documentation you can refer to. There is this that will open up later, and there is the founder's GitHub, or the creator of XGBoost, and also the GitHub that is Distributed Machine Learning Club, if I remember correctly, that actually hosted the XGBoost codes here. Now, gradient boosting really is proposed in the paper Greedy Function Approximation, a Gradient Boosting Machine by Friedman, which is what we actually covered earlier. Now, XGBoost is actually based on this original model and is supervised learning. So let's just start with the objective function. Now, ultimately, when you're actually doing any machine learning, you will always have two parts to it. One is called L, the training loss function, and the other is omega, which is the regularization term. Each has its own function and the purpose. The training loss function is a measure of how predictive our model is on the training data itself. Now, take, for example, linear regression. This is what you will use, your observation minus the actual mean itself and square, and basically you're trying to minimize this loss term. For logistic function is this one here. Ultimately, again, you're looking to minimize the loss term. So that's really the purpose of the training loss, is to actually, you keep tuning this until it is predictive, okay, or highly predictive, or the accuracy for classification-based machine learning, it becomes as best as it could. But there is also a problem, is that when you actually only focus on that one side, your model can overfit your training data. Hence the reason for the regularization term. This part here controls the complexity of the model to avoid the model being overfitting the actual data itself. Now, that's really a very gentle and brief walkthrough, just so that you can actually quickly come to speed with what XGBoost is. What I want to do now is just to actually show you a little bit of the documentation itself. That's the link that I've given to you earlier. Now, come to XGBoost documentation. So this is the actual website itself. Feel free to actually go through this a little bit more. There are a lot of the contents that's really useful. So what I want to do is actually specifically go to one of the tutorials, okay, just to explain it from the first principle so that you understand a little bit. And it basically is an expansion on what we actually talked about last time, which is the boosting. But nevertheless, it's a good idea to actually walk through this so that you understand the strengths and why it works so well. So now we have a tree ensemble. Now that we have introduced we talked about supervised learning, we're looking at the tree. Okay, so remember classification and regression tree that we talked about. What we have here is this. You have an input features. You have the age, the gender, the occupation, on and on it goes. So the question now is that, does the person like to play computer games? That's really the question that we want to actually answer. So the tree may actually form or come to this kind of formation whereby is the age less than 15? Yes. Is it male? Yes. Okay, then the actual prediction score in each leaf will be +2 here. And for the female, +1. So this portion actually likes to play computer games. And then the no part here is -1. Okay, so that's really the prediction score. Now we classify the members of a family into different leaves and assign them the score on the corresponding leaf. So basically the classification or and regression tree is a bit different from decision trees where the leaf only contain the actual value itself. In CART, a real score is associated with each of the leaves, which gives us richer interpretation that go beyond classification. This also makes the unified optimization step easier, which I won't go in, but you can read it in here. Now, the unfortunate part about a tree is that it's not strong enough to be used in practice. So what is actually used is so-called a tree combine, okay, or ensemble tree, which sums the prediction of the multiple trees together. So you have the tree, first tree that we looked at earlier, and then you have this second tree, which look at one feature, all right, which is do they use computer daily? If it's yes, okay, the prediction is +0.9. If it's a no, it's -0.9. So for the function of this boy or this young boy, which is under 15 and the male, is 2 + 0.9. So that gives you 2.9. How about this old gentleman here? So you have that -1 and -0.9, so it's -1.9. So this is really an example of an ensemble of two trees. The prediction score of each individual trees are summed up to get the final score. If you look at the example, the important fact is that the two trees try to complement each other because we are using different features. Now I won't go through the mathematical function, but this one should be quite familiar to you. I went through it earlier. You have the loss function here, and over here you have the regularization function. Okay, so now let's go into tree boosting. Having done the initial introduction, now let's begin with the real training part. Now how should we learn the trees? The answer is for all supervised learning models, we have to define a function, objective function or loss function, and optimize it. And there we go. That's this part here. That's what we're actually trying to do. And also use regularization to control the overfitting problem. Okay, additive training. Okay, the first thing we want to ask is what are the parameters of the tree? You can find that we need to learn are those functions fi with each containing the structure of the tree and the leaf nodes. This is much harder than traditional optimization problem where you can take the gradient and go. It's not easy to train all the tree at once. Instead, we use an additive strategy, fix what we have learned, and add one tree at a time. So remember that we talked about this earlier on, really regarding boosting. You actually keep learning and just learning from the previous lesson that you've learned. And again, this one here, every instance, every time you learn from the previous lesson that you've learned or learn from your previous mistake. Okay, so let me close that so that we don't have too many tabs. So fix what we've learned and add one new tree at a time. So let's just say we write the prediction step at step t as y hat to the power of t, so that y hat, the step 0 is equal to 0. And the prediction of step 1 is equal to function 1, which is the previous 0 step plus function 1. And step 2 is basically function 1 plus function 2 is equal to this original one, which is this one here, plus function 2. So on and on it goes. It continues on this way. Now, the important part is to actually understand that we are continuously trying to fit this so that ultimately we're trying to minimize this, or basically optimize is the other word, or minimize the loss function. Now it remains to be asked that which tree do we want at each step. A natural thing is to add the one that optimizes our objective. Now if we're using mean square error as our loss function, then it comes with the following form. Again, I won't go through these in details. I'll let you read through them. So this ultimately, after much math, this become our optimization goal for the new tree. The one important advantage of this definition is that it only depends on two things, the g function and the h function. And this is how XGBoost can support custom loss function. We can optimize every loss function, including logistic and weighted logistic, using exactly the same solver that text GI and HI as input. Now we've so far talked about how to optimize, but what we haven't talked about is the regularization step, okay? Meaning managing the complexity of your model. Okay, so within this part, what do we have? Okay, what you have here, let's look at the definition, is the omega. In order to do so, let us define the definition of the tree as this following. You have a weight, okay, it's a real number, and it's transformed the R to 1 to T. So where W is the vector of scores on the leaves itself, which is this one here, Q is the function assigning each data point to the corresponding leaf, and T is the number of leaves. In XGBoost, we define the complexity as that. Now, of course, you can actually define it any way you like, but this specific one works well in practice. I won't, unless you know what you're doing, for now, I'll just leave it as it is. The regularization is one part most tree packages treat less carefully or simply ignore. This is because the traditional treatment of tree learning only emphasized improving impurity, while the complexity control was left to heuristic. Okay, right, so we've done a whole lot of definitions here. I think it's before we actually go into the practice part or applying part, the part that's really important to understand is the basic fundamental principle, which we talked about in detail. Now, gradient boosting machine literally is sequentially adding predictors, same as gradient, extreme gradient boosting. All right, and each one correcting his predecessor and continuously so, and keep adding as we go. So one key thing that I really want to emphasize that the gradient boosting do not have is really this regularization term. Now I'm gonna show you the answer from Professor or Dr. Chen. This is what he say. What is the difference between the RGBM or gradient boosting machine and extreme gradient boosting? So this is what he say. All right, they've both followed the principle of gradient boosting. There are, however, a difference in the modeling details. Specifically, XGBoost use a more regularized model formalization to control overfitting, which gives it a better performance. We went through the introduction to boosted tree, so feel free to read that again. So this is what he actually ultimately called. For model, it might be more suitable to be called as regularized gradient boosting. So in essence, this is actually gradient boosting, but there is an additional term there which controls the overfitting, which is the regularization part. Now, with that, let's look at doing some code. It will be helpful to actually get some intuition on that. Okay, what I've done is actually I've added the definitions here that we just went through so that you can actually refer to it easily. Okay, so what do we do next? I wanted to go through the extreme gradient, and so far we've spent a lot of time on understanding the Titanic data. So I'm going to continue with the theme of the Titanic data, just so that you can actually compare the performance and understand the step that actually related to the extreme gradient boosting. So let's look at this. Data frame is equal to the SNS, and we're going to load the data set Titanic. All right. Okay, so we're gonna drop not a number and remove them all together. Now we're gonna do some data pre-processing before we proceed further. So we remember that we look at the passenger class, and we also look at their gender, and the last thing that we also look at was their age. And we'll do some processing, import the pre-processing, and we also instantiate this pre-processing, and we're gonna change the binarizer, and we're gonna convert the gender into fit transform X. Okay, right, that's fine now. Right, the next thing is that we do need the actual class itself survived. Okay, right, let's break this up, and we're gonna split our data now into training and also test data. So from From sklearn, model selection, we're going to import train test split and set this up so that store the splitting train and y test. Let's go to the train test split, and we're going to put in x, y, and the test size, we're going to leave it at 30%. Okay, now we need to, let me import the file of cross-validation score, accuracy score, classification score, as well as the confusion matrix. We wrote this function earlier to do this, so I don't have to rewrite them. Right, let's run XGBoost as the workflow, and let's have a look at how well it actually performed against the rest, and also to understand a little bit in terms of the workflow itself. So XGBoost as XGB, and the next thing is XGB classifier is equal to XGB, the X right classifier, and we're just going to set pretty standard parameters, number of estimators is equal to, let's just put it as 5,000, and the learning rate, let's just use 0.2. XGB CLF fit our X train and Y train. Alright, having done that, so let's have a look at the score itself. So we're gonna just, okay, so we're just gonna print this lot here. So first thing is we need the classifier's name, CLF, and the rest are the same. Okay, 9370, the accuracy score is that. Okay, so let's look at, change the training to null. Now we are looking out of sample, so we get 7273. Now let me just pull the data of what we did previously, just so that you can actually compare the performance. Let me have a look, see if I can actually bring that across for you. Give me a sec. Alright, what do we have here? Looking at the score here, we scored 9370, which is middle of the road. More importantly is the average accuracy, which is 76, okay, which is about middle of the range, and the standard deviation is also middle of the range, and the result is also middle of the range. So nothing really exciting. I think what I mentioned before, I'll just reiterate the same point here again. It might very well be that we don't have enough data to really assess the model, but that's okay. At least we now understand the actual process flow itself. We have a better grasp of it now, of how XGBoost works. Now before we wrap up this lesson, I'd like you to actually do a practice exercise. And just over here, what we did is actually, we have the maximum depth is equal to 3. I'd like you to actually change it to 5 and see what kind of result you will get. Maybe change the estimators to 10,000 as well, and learning rate increased it to 0.3. Now pause the video, give it a try. When you come back, and I'm going to wrap up the lesson. Now how did that go? I hope it went well. At least you've given it a try, and at least experience the actual process flow itself. I tried it as well. The accuracy score didn't change too much. The average accuracy score though has actually improved somewhat. The standard deviation has dropped a little, but the out of sample result is still not impressive. And when we come back, we're going to apply all of the models that we've learned so far, from covering the different ensemble models, and we're going to go through them all, applying to a completely different data sets, this time around with much more data, which is an extension of our previous model projects called the Human Resources Analytics Datasets. I look forward to seeing you then.